Jordan.
I'm Jarrell Alicki. I worked on the timing platform over the summer with AGML. This was developed as a way of benchmarking the math functions we were writing for the adaptive math library. During the summer, it was called Timing Framework. It's actually going to end up with a new name eventually, once I come up with something that's catchy and marketable like this does. So the timing platform is a utility for benchmarking small segments of code. It's designed for really like math functions, so something that maybe consists of between 10 and a few hundred lines of C++ code. Over the summer, it was developed as a standalone application, which it worked, but really we were doing all of our development in IDE anyway, so if we could integrate into that IDE, it would make it a lot easier to use. It's, however, not a code profiler. When you think of benchmarking code, a lot of people will automatically think, oh, code profiler. However, a profiler just indicates bottlenecks in a program. This allows you to get very detailed statistics on a small part of the program. So if you use a code profiler and find out, oh, this function is running really slow, you can then use timing platform to determine why it's running slow, whether you're cache missing, exactly how many cycles it takes, statistics like that. So it times code. It uses the hardware performance counters. And basically, these counters are always logging statistics about whatever is being executed on the processor. This just pulls some of that data off the processor and then analyzes it and displays it in a user-friendly manner. And it can display everything from instructions executed, fused macro operations, cache misses, cache loads, branch mispredictions, clock cycles, resource stalls, basically any statistics that you could really need for analyzing why a piece of code is running slowly. So over the summer, it definitely worked. It was able to time our functions. We were able to benchmark everything and find out how many CPU cycles it took for each math operation. However, the user interface was not all that great. It had a very complicated setup, and on Windows 7, it usually worked, but it required you to be running in test mode and then jump through a bunch of hoops to get the drivers installed. It uses some drivers that are developed in assembly, and they work to lock a thread to a CPU core. And it was the old implementation of it was very slow. It required at least 6 to 10 seconds per test run, which if you want to benchmark a lot of math functions adds up very quickly. It was inconvenient. Code had to be copied and pasted into the interface, and it was a standalone application, but it required Visual Studio. You used some Visual Studio intrinsics, so you had to use it on a computer with Visual Studio installed anyway. This is what it looked like over the summer. It's rather intimidating, and it was a pain in the neck to use. The new look for it is this. So basically, you select code in your current application in Visual Studio, right-click on it, and then in your context menu there will be an option called Timing Platform. When you select that, the code you've selected will be pasted in here, and it lets you do that several times so you can collect multiple functions for testing. You have to, right now you have to manually input a post-test to prevent optimization out of your functions, but that's going to be implemented by the end of this semester. And then the run benchmark thing is greatly simplified, and all of those paths that you previously had to manually specify are now automatically detected. And a lot of the settings are automatically detected when the plugin starts, such as the time delay needed for the compiler to run. So right here, I have 3 different functions, 3 different snippets of code loaded here. There's a for loop for int a equals 0, a is less than 1,000, and then increments a, and then it's int b is plus or equals a times b. So it's going to run through this code 1,000 times. The second function I'm testing is a standard cout hello world, and then I'm doing standard printf hello world. And it's interesting, the results you get, it shows how bad cout is really. So if I'm testing on the reference clock cycles, number of instructions, L1 data cache misses, and L2 cache requests, and then look at the results, We saw the for loop ends up as 4,005 instructions and around 30,000 clock cycles. The cout is around 43,634 instructions, and it's around 80,000 clock cycles. However, the printf hello world is only 5,210 instructions and around 8,000 clock cycles. So this sort of utility is very useful for determining when you write an optimized version of a function, whether your optimized version is actually faster than your original version. So right now what's finished is the timing components in the back end have been extensively tested and developed this semester. And there's a rough user interface front end. For the rest of the semester, I'm going to be continuing Windows 7 compatibility, making it work and be easier to set up. It's going to have a way of logging results over time, so it'll keep a database with a program file, so you can see, 2 weeks ago this section of code took this many cycles to operate, now it's this much faster, this much slower. And it's going to be more tightly integrated with the Visual Studio IDE. And this is a mock-up of what it's going to look like. This has been tested right now. It's not entirely stable, so it's not in the current build. But this will give you color-coded from green to red of relative speed. So just at a glance, you can see which lines of code are taking the most time to execute. So, yeah, that's about it. Is there any questions?
Is this just for benchmarking C++, and do you have to use Visual Studio to use it?
Currently, you have to use Visual Studio. However, I've been implementing some of Intel's Performance Counter API stuff, which will allow it to be used on Linux, Mac, and Windows for some of the functionality. So it'll be cross-platform, but to use all the functionality that's currently available in it, it would have to be done using Visual Studio.
And you need to use C++ to benchmark?
Currently, it supports C++ and assembly. I'm going to be simplifying the way you use it with assembly language. So. But it's really designed for C++.
Is there any way to review those results tables like side by side so you can compare?
There's not. That's one of the things that's going to be added.
Okay.
So you select code and you right-click in the context menu and adds it. Is there a way to test it for different inputs? Because I can imagine like different trig functions, depending on what you input, it would take different amounts of time.
There currently is not exactly. However, there is a way to initialize any variables to a value.
Okay, so you modify
so you could manually input things.
And are you going to add like scripting functionality so you can have it automate?
It wasn't something I was planning, but it's a good idea. It does currently have a command line interface too, so you can write some sort of script that would automate it yourself. I mean, I imagine that would be a very application-specific thing.
Just out of curiosity, how reliable are the benchmarks? Like if I were to use a different benchmark plugin, would I get similar numbers as basically my plugin?
You should. It's using the hardware counters, so as long as you're on the same physical CPU and it's running at the same clock speed, because like Intel CPUs have speed step and that sometimes interferes with things. But if you're running on the same hardware platform, your results should be very close. The only real inaccuracy in it is it works with a timing loop, so it subtracts the overhead from the timing loop. That overhead is calculated at the beginning of the plugin run on a given hardware platform. So if you happen to have a bunch of other applications running, and they happen to be on the same core that this is running on, and they happen to be using the processor at the time when it's trying to calculate that overhead, you can be off by maybe 10 or 15 clock cycles, which really is not all that critical if you're benchmarking a function that's going to be on the order of like 50,000 clock cycles.
Thanks.